Alright, so today we're going to work some problems involving average rate of change, instantaneous rate of change, and just some basic ideas of approximating limits numerically and graphically. So we're going to start with average rate of change. I have the formula here for you. It's just the slope of the line between the 2 points. So now let's look at this example. So we have a ball that's thrown upward. There's the initial velocity. Here is our formula. So this formula will give us height if we plug in time. And we want to calculate the average velocity between 0.5 and 0.25. So these are going to be our x1 and our x2. Doesn't really matter what order we put them in, but that's kind of the order that I go in, left to right. So if we want the average, I'll write it like this: average velocity between 0.5 and 2.5. Then what we want to do is we want to take our height equation and we want to find the height. Sorry, let's actually write it like this: the height when t is 2.5, so it's h of 2.5, and then subtract the height when t is 0.5. Divided by 2.5 minus 0.5. So we're going to plug these into the function. I'm pretty sure you guys know how to find function values. So for h of 2.5, we get 6.875. And for h of 0.5, we get 6.275. And all over, that's going to be 2. So then we end up with an average rate of change between 0.5 and 0.25, 2.5, saying that. It's going to be 0.3. Let's make sure we put the units on it. Told us it was in meters and seconds. So this is going to be meters per second. That's 0.3. Make sure you always write your answers as sentences, so not just naked numbers, but you are writing a math sentence like we wrote here. So now let's think about instantaneous velocity. So all we do for instantaneous velocity is we have other methods that we'll talk about later, but at this point the only way we can do it is numerically. So we just want to take tiny little average rate of changes, I guess, really close to the value where we are wanting to calculate the instantaneous velocity. So here is at 1. And what the instantaneous velocity is what's called the tangent line. And that is the line that's just going to go through that point and skim the curve. And so we're interested in the slope of this line. What we calculated earlier, this is called a tangent, is what's called the secant line. And we did right about there. Let's see if I can get this right. It's right about there. That looks pretty good. And this is when it crosses through 2 points of the function. And the tangent line is where it just skims. So we want to calculate the slope of that tangent line, or the instantaneous velocity, when t is 1 second. So we're going to take and we're going to make these tiny little intervals around t. And this is what they'll look like. So we're going to look at the interval of the average rate of change over the interval 1 to 1.01. And then we're also going to do it again. This is what I call the right-hand side, 1.1 to 1.001. So generally you want to do a couple on the right-hand side and then a couple on the left-hand side. So this is right. And now over here is going to be left. So same idea, but now I'm going to do 0.99 to 1. And then the next one is going to be 0.999 to 1. And so I'm really just calculating the average rate of change over these intervals. So I'm using this formula I just used a second ago. We're still talking about throwing that ball up in the air. So we're still using that h of t formula we used before. This one is going to be Same deal. I'm kind of cutting a step out by going ahead and subtracting there. For 0.99, it's going to be h of 1 first. I usually do the bigger on the left-hand side, minus h of 0.99 all over 0.01, and then h of 0.999 minus h of 1 all over 0.001. And then I'm going to plug in and do all the math. For the first one, I get 10.15151 minus 10.1 all over zero point zero 0.01. And then I do that math and I get 5.151. All right. If you guys want, you can pause and calculate the rest of these yourself. Come back and I'll give you the answers, or I'll just go through and give you the answers. So here is, if we find our function values and do the math for 1.001, we get approximately 5.2. If we do this one right here, and we get 5.249. When we do the last one, we get 5.205. Notice they're approaching both from the left and the right. This one was a little smaller than 5.2, and then this one got closer to 5.2. This one was a little bigger than 5.2, and this one got closer to 5.2. So it's always important to come and look at both sides when you're approximating instantaneous velocity, instantaneous rate of change, because it could do something different from one side versus the other, and you really want to think about approaching from both sides. So what we can say here is we can say that the instantaneous velocity at t equal 1 second is approximately 5.2 meters per second. And you know, you can always, if you think you may have gotten a funny answer, look at the graph. You know that instantaneous velocity is the slope of that tangent line. And I think I mean, my graph is not perfect, but I would say that I can see that has a slope fairly close to 5. The blue line that I have right here, that has a pretty flat slope, and we only got the slope of that line to be 0.3. So always try to put it in context. If you can look at a picture, anything you can do to help yourself. So now let's talk about limits and approximating limits. So look at this example, what I've written right here. So when we calculated the instantaneous velocity at some value, say t equal 1, t equal 2, whatever, all you're really doing is you are calculating this limit right here. And really, the very first look at limits we have is by calculating instantaneous velocity and trying to get the slope of that tangent line. It's going to be really important when we study derivatives later, because a derivative is really just a limit. Um, but first, we're going to learn how to calculate limits. So we're really going to come back to this idea right here, this formula, when we talk about derivatives. But just to kind of show you where we're coming from, here is the formula for instantaneous velocity using limits. What we did when we calculated it from both sides is, and you can use notation like this. You see that little mark next to the O on the limit? That would be from the left when it has that negative sign on it, because you're below 0 and you're calculating those intervals below. So when we're coming from the right, we use notation like this with a little plus. And this would be a limit from the right. And when there's no notation there, then we're looking at the limit from both sides. If that's not equal, then it doesn't exist. But we'll talk about that in just a minute. So I have an example for you here, how we're going to approximate this limit numerically. We have the limit as x approaches 0 sine x over x. Now, I could look at this immediately and see that because of the formula that I have, x really can't be 0 because it's in the denominator. And there's no way to cancel or make it so that x isn't in the denominator. It's just what we have. But maybe there is something going on the left side and the right side, and they're both coming to the same number, even though we have the issue with 0 right here on this function. So we are going to take and we're going to look at values really close to 0 from the left and the right. So I could say like negative zero point 0.1, negative zero point 0.001, negative zero point 0.0001, and so on. And then for the right, I could say positive zero point 0.1, zero point 0.01, zero point 0.001, zero point 0.0001, and so on. I skipped one here. You always want to make sure you look at what's happening on both sides whenever you are approximating a limit numerically, because sometimes they can do very different things. So we plug and chug, and we want to see what these values are. So this is what I get. I got 0.99833 for negative zero point 0.1. I got 0.99998. I mean, I think it's kind of obvious as long as it's doing the same thing on the right-hand side what's going on here. But I'm going to keep going just to make sure. So for negative zero point 0.001, I actually get 1. And I'm going to say, though, it's approximately 1 because I think that my calculator is cutting off the decimal too much and rounding for me. And then I actually get 1 again. So I'm going to say approximately 1. Now I'm going to go over to the right-hand side. I'm going to plug and chug on this side. So this is 0.99, same thing actually, 833. It's nice. It looks like it's doing the same thing on both sides. Let's try the next one. So this is going to be 0.99998. Awesome. So then when I do 0.001, I actually get 1, but I'm approximating here. Nothing's exact, so I get approximately 1. So on the left-hand side and the right-hand side, I get the same thing. So this is the value of my limit. This is the approximation. And so I could say up here that the limit as x approaches 0, sine x over x is approximately 1. And I believe sometimes they'll ask you to show it numerically. So this right here, what we just did is to approximate it numerically. And then sometimes they'll ask you to approximate it graphically. And so here is a graph of sine x over x. Oh, I do that all the time. Sine x over x. And this is negative, or 5 to negative 5 down there, and then this is 2, and I think that's negative 1 there. So you can look at the graph, and you can see, look and see what happens from the left as x approaches 0. If this is 2, obviously that's going to be 1. So I can see that the limit as x approaches 0 from the left of f of x is 1. And then I can also see on the right, as I'm approaching this way, that the limit as x approaches 0 from the right is also 1. And so then I could say from the graph that the limit is approximately 1. If they ask you to choose whether you want to do it numerically or graphically, make sure, if you choose graphically, that you sketch a decent picture of the graph so that I can tell that you know what's going on. And make sure you indicate, maybe in a similar way that I did, that you know that the limit from both sides is the same number and it's actually, some value. So I told you just a second ago that in order for those no, that if those two things existed, if no, sorry, Lord, if those two things were equal, then the limit would exist. So here's kind of a little, really short and to the point definition, how a limit exists. You look at the limit from the left-hand side, and it's equal to the limit from the right-hand side. That doesn't always mean that the function is defined at that point. So say you have some funky piecewise function, and it's got this little hole right there. I don't know if I can do that. Let's try. That worked out. And maybe that's it too. And instead of it being defined as 1 at 2, it does something like this. Now, if I look at the limit as x approaches 2 from the left, it actually is approaching 1. Even as close as I can get, not exactly on 2, it's still going to be 1. As I approach from the right, it's still going to be 1. So this limit exists. The limit as x approaches 2, and it would be equal to 1. It doesn't matter what that function is defined at. One thing about how a limit truly exists is that it's finite. And sometimes students struggle with this because sometimes you'll see a question where if the limit as x approaches from the left and the right is the same, but it's infinite. So say if we'll look at this example in just a second. So maybe if we look down here and we look at this would be 1 over x squared. The limit from the left we would call positive infinity. The limit from the right we would call positive infinity. And you may even see an answer on a multiple choice question that gives you positive infinity, and that's the correct answer that's approaching on from the left and the right to the same value. But, well, see, I said that and I shouldn't have, because this really isn't a value. So you really can't say that the limit exists. Now, here are 2 examples right here where the limit really doesn't exist. Sounds kind of silly to say it that way, but if we look at the one on the left, x over the absolute value of x, as I approach from the left, I'm approaching negative 1. As I approach from the right, I'm approaching positive 1. Here's 1 over x. As I'm approaching from the left, I'm approaching negative infinity. As I'm approaching from the right, I'm approaching positive infinity. So that doesn't exist. Now, estimating limits from a graph is really easy. You just kind of go a little to the left of the point, run your finger along, see what's happening. So here I have an example. Don't get so confused with all the dashed lines. I'm going to use some colors that will make it a little easier. But I want to determine the one-sided limits at 1, 2, 3, and 4. And then I also want to determine whether the limit exists. So I'm just going to make a little table. And then I'm going to do it for 1, 2, 3, and 4. There we go. So we don't have to write all that notation. I mean, it's beautiful notation. It makes a lot of sense. You can write a lot of math sentences and not a lot of words, but this still explains everything I need to explain. All right, so now let's take a look at the left. So here, we'll start at C equal 1 from the left. So I find C equal 1 right there. So I'm going to go take my function, travel along, and as I'm approaching from the left, I'm approaching 2.5. Now I try from the right. So I go find the function to the right of 1, and I travel back to 1. And I'm also approaching 2.5. So since these 2 numbers are equal, then the limit exists. Now let's try 2. Switch colors on you. So for 2, if I approach from the left, approach this way, and I'm approaching 3. Now if I find my function, if I approach 2 from the right, I'm approaching 2. These things are not equal, so no, this does not exist. Alright, so now I want you guys to pause the video, do the other 2, come back to me and I'll give you the answers. Alright, here you go. This one is 1 and 3.5, so these things are not equal, and that doesn't exist. The last one is 2.5 and 3, and these things are not equal, so that one doesn't exist also. Alright, I hope I was of some help. Thanks, guys.